We are starting off with objective number 3, which says to interpret symbols in chemical equations, such as those relating to states of matter or reaction conditions. If you find your unit objectives sheet, the purple piece of paper with the objectives for Unit 10, you'll find on the back of this a chart that looks like this, Table 11.1. And on here it has some definitions of some symbols that you will see in chemical equations. So we're going to go over this now. The symbol that is used to separate two reactants or two products is a plus sign. The symbol that means yields and separates the reactants from the products is an arrow sign, like so. Now, some chemical reactions are reversible and can go both in the forward direction and in the reverse direction, in which case we would use a double-headed arrow, or as you see here, two half arrows pointing in the direction. If a reactant is in the solid state, we put an S in parentheses as a subscript after the formula. So S stands for solid. If there is a reactant or product that is in the liquid state, we would use a lowercase l in parentheses as a subscript after that particular formula. So L for liquid. If the reactant or product is in the gaseous state, you probably guessed that this will be a G in parentheses as a subscript after the formula, so G for gas. Now, if a substance is dissolved in water, it is considered to be aqueous. This symbol is an AQ in parentheses, written as a subscript. So aqueous, which means it is dissolved in water. Let me scroll down so we can see the rest of this chart better. If heat is supplied to the reaction to make it happen, there's one of two ways that we can indicate this, and both of these symbols are placed on top of the reaction arrow. If you can just write the word heat over the arrow, or you can use the Greek letter delta, which is simply a triangle, and this means heat is applied, and you would write either of those symbols directly over the arrow. If you see some sort of element symbol or chemical formula written above an arrow, what this implies is that this substance, in this case platinum, it is used as a catalyst. So if the catalyst happened to be iron, then you would see instead, you would see an arrow with the Fe above it. If the catalyst was manganese dioxide, you would see MnO2 as the formula written above it. Okay, so those are appropriate ways to write catalysts in an equation. What you should not write, unless it's very, very vague, if you write just CAT or catalyst over the arrow, that is not adequate enough, because most often the catalyst will be specifically told you what it is. So just writing catalyst or cat over the arrow is not good enough. All right, we're going to go back to objective number 2, which says we are going to translate chemical word equations into skeletal equations. All right, so a couple things to define. A word equation is essentially a descriptive story of what's happening in the chemical reaction. And a skeletal equation is when you have correct chemical formulas, when you have correct states of matter, and when the heat and or catalysts are indicated. Okay, so that's what that means to write a skeletal equation. What this does not mean is skeletal equations are not balanced. These are not balanced equations. That's another topic that we will get into after we are comfortable with writing skeletal equations. So I'm just going to write this in as not skeletal equations, or not balanced equations. All right, so what we're going to do is we're going to take a look at 5 chemical reactions here, and we are then going to write the correct chemical reactions or equations for them. This is a solution of lead to nitrate, which is a clear, colorless solution. and it is combined with a solution of potassium iodide to produce, which is also a clear colorless solution, to produce aqueous potassium nitrate and a yellow precipitate named lead-2-iodide. So that yellow cloud you see is the yellow precipitate called lead-2-iodide. So that's the chemical reaction. You're witnessing it here. This is a reaction that produces, it's fairly hazardous materials, so we don't do this in the classroom because the nitrates are fairly toxic to work with, and the lead iodide is a hazard to in the landfills. So we don't do this reaction in class. But it's kind of interesting to see because what you can actually see here is the precipitate. A precipitate is when, you might want to write this down as a definition. A precipitate is when a solid forms when two solutions are mixed. Okay, so the key thing here, when you see the word precipitate, you know that that product is going to be solid. All right, so let's take a look at this equation written over again, and what we're going to do is we're going to start by writing the chemical formulas for the reactants and the chemical formulas for the products. All right, so you have to identify who are the reactants and who are the products. So it says a solution of lead-2 nitrate is combined with a solution of potassium iodide. So those substances are your reactants. And then I see to produce aqueous potassium nitrate and the yellow precipitate lead-2 iodide. So those are our products. So now at this point, to write the chemical formula for our two reactants, our lead-2 nitrate and our potassium iodide, it might be handy to have out your ion charts because we're going to need those ion charts in order to crisscross properly. So starting with lead-2 nitrate, lead-2. The symbol for lead is Pb, and 2 means it's a +2. Nitrate is the ion NO3 with a -1. So crisscrossing that, we get the chemical formula Pb, NO3, 2. Now, this says that this was a solution. And so when you see the word solution, that solution implies, and it's not showing up very well there, it implies that the substance is aqueous, that it is dissolved in water. So that's going to be really helpful. When you see the word solution, you'll know to put the aqueous symbol after it. Okay, so there we have our first reactant. Our second reactant is potassium iodide, right here, potassium iodide. Okay. So potassium iodide is K, potassium, which is a +1, iodide, which is the symbol I with a -1. So crisscrossing, the symbol is just Ki. So I'm going to bring that down here and clean it up, just like so. And it is also a solution, which means we can put an AQ next to it. Okay, so those are our two reactants. Really the only thing we need to do here is put a plus sign between them to show that those two reactants will react together. At this point I'm going to put an arrow to indicate that we're going to have some products. So let's take a look at our products. There are two products here, potassium nitrate and lead-2 iodide. So let's start with that potassium nitrate, and I'm just using this top half area up here to do my little scratch work with my ions. So potassium nitrate, potassium is K with a +1, nitrate is NO3 with a -1. So +1, -1, pretty straightforward. This formula is KNO3. Now, if we go back and take a look at the state of matter, it is aqueous. So that means I'm going to put a little AQ there. Our other product is lead-2 iodide. Lead-2 is Pb +2. Iodide is the I with a -1, so crisscrossing. we get PbI2. Now, it says that it is a precipitate, so that means it is going to be a solid, so I'm going to put an S here, kind of going off on the side here. That's not very clear. Make that a little clearer. Right, so an S right there. And then really the only other thing I need to do here is just put a plus sign between the two products to indicate that those are two separate substances. Right. So this is a skeleton equation. So what we have done is we have indicated the proper chemical formulas and the states of matter for this chemical reaction. This is aluminum foil. It is placed in a flask containing chlorine gas. White powdery aluminum chloride is produced and a large amount of heat is released. I'm going to go ahead and play that again. There goes the aluminum foil. The chlorine gas was already in the flask. You can see a white powdery substance evolve, as well as the very bright white flash. Okay. So if we were to write this out as an equation, first we want to identify our reactants. We start out with aluminum foil being placed in a flask containing chlorine gas. So those are our reactants. White powdery aluminum chloride is produced and a large amount of energy is released. So those are our products. So let's start with our reactants. Aluminum foil. Aluminum foil is just the element aluminum. So that's pretty simple and straightforward. We're just going to write Al. Now because it's a foil, that's going to tell us that it's a solid. The other reactant is chlorine gas. Okay. Chlorine gas. Chlorine is one of those diatomic elements. When chlorine is in its elemental form, it has to be diatomic. It has to be Cl2. So that's something you're going to have to become very comfortable with, that when you see chlorine, you're not going to put just Cl. You're going to do Cl2. It is a gas, so that's very straightforward. We're just going to put a little G sign there. So those are our two reactants. I'm going to separate them with a plus sign. And I'm going to put an arrow to indicate that those two reactants are going to form the products that we're going to now write. It says a white powdery aluminum chloride is produced and a large amount of energy is released. So really we only have one product here, and it's the aluminum chloride. So let's start with writing that formula. So aluminum is a +3, chloride is a -1. Crisscrossing, that formula becomes AlCl3. Okay. So it is a white powdery substance. Powdery indicates that this is a solid, so we're going to include it as a solid. Now, we haven't seen any indication of a catalyst on either of the first two reactions, but we are seeing here that there is energy being released. And so when energy is released, that means it is a product. And so typically we would write that as heat or energy. So I'm going to put both of those terms right here. Heat, energy. If you wrote just heat there or just energy, that would be also appropriate. Now, heat energy is not a substance where you would put a solid, a liquid, or a gas symbol after it, so you don't have to worry about the state of matter there. So this right here is our chemical skeletal equation for this second reaction. Let's take a look at our third reaction. A drop of water is placed on a lump of sodium metal. Heat is produced, as well as sodium hydroxide and hydrogen gas. Alright, little technology snag here. Here I've got the video queued up again, so let's take a look at this video. This is water being, drop of water being placed on a lump of sodium metal. Energy is released, as well as aqueous sodium hydroxide and hydrogen gas. Okay, so there's the water being dropped on the sodium metal. And you've actually seen this reaction before in class when we actually took the sodium metal and put it into a beaker of water. So you have seen this one before. So let's then take a look at writing out this equation. A drop of water is placed on a lump of sodium metal. So that right there are our reactants. Energy is released, as well as aqueous sodium hydroxide and hydrogen gas. Those are our products. So let's start by writing our reactants. A drop of water. Okay, so water, as you know, that's our first reactant, which is H2O. And it's a drop, which implies that it is liquid. So I'm going to do L as a little, as a cursive L. If you write it just as a straight line, it tends to look like a number 1. So we're going to do a lowercase l as italicized lowercase l. It is placed on a lump of sodium metal. So sodium metal is just the element sodium. So that's just going to be Na, pretty simple and straightforward. Lump implies that it is solid. Right, so those are our two reactants. I'm just going to put a plus sign to indicate the separation of those two reactants and an arrow to indicate that the reaction will move forward and produce the products, which we will now figure out now. There are two products here. Sodium hydroxide is one and hydrogen gas is the other. Sodium hydroxide, this is an ionic compound which we will need to write the formula for using crisscrossing technique. Sodium is a +1. Hydroxide is OH with a -1. So crisscrossing, you just need one of each. This is NaOH. Now, it's told that this is aqueous, so pretty simple and straightforward. You just put a little AQ there. Hydrogen gas is our second product. Hydrogen gas, this is one of the 7 diatomic elements, which means you're not going to write this just as H. This is going to be H2. It says it's a gas, so we're going to put the little G there. We'll separate those two products with a plus sign indicating that there's a separation of those two products. Now there is energy being released, so we should also include here, now I'm going to have to put it down on the second line, that energy is being released over here. So it would be best if we could put that all in one straight line, but apparently I didn't leave myself enough room. So this is our skeletal equation for reaction number 3. Let's take a look at the fourth reaction. Nitrogen triiodide, which is a red solid, is a contact explosive that rapidly produces nitrogen gas and iodine powder with a touch of a feather. Here it is in slow motion. And we're going to slow it down one more time, even slower. And you can see it does not take much to trigger this particular reaction. So let's take a look at writing out this particular equation. Nitrogen triiodide, a red solid, is a contact explosive that rapidly produces nitrogen gas and iodine powder with a touch of a feather. So here, this is an unusual one, is in that there is just this one reactant. So, and then it says it rapidly produces nitrogen gas and iodine powder with a touch of a feather. Okay, so those are going to be our products. Oh, I think I did this with my colors reversed. Sorry about that. Okay, so the reactants I've labeled as R, and the products I've labeled as P. Alright, so nitrogen triiodide. This is a covalent compound, so you notice the use of the prefix. So the name very easily tells us the formula. So this is N for nitrogen, triiodide meaning 3 iodides. So nitrogen triiodide, which is a red solid. Okay, so we're going to put S for solid. It's just the one reactant, so immediately I'm going to go ahead and put the arrow indicating that products are going to be produced. It produces nitrogen gas and iodine powder. Okay, nitrogen gas. Again, nitrogen is one of these 7 diatomic elements. So N2 with a G. Iodine powder. Iodine, again, one of the 7 diatomic elements. I2. It's a powder. So so we indicate that with a solid. I'll put a plus sign between those to indicate that there were two separate products produced. And definitely heat was released, so I'm going to indicate that here. Lost my pen for a moment. Plus heat energy. But in order for this to happen, we had to indicate a tiny little trigger of friction energy, which I'm going to indicate with a delta sign to show that a little bit of heat in the form of friction had to be applied in order for this reaction to move forward. It doesn't take much, as you saw. The fifth and final chemical reaction that we're going to write an equation for today is this one. Carbon tetrahydride gas, commonly known as methane gas or natural gas, is bubbled through dish soap to create a mound of bubbles. When ignited, a large amount of heat is produced, which vaporizes the water and carbon dioxide products. All right, so pretty spectacular reaction there. Let's identify the reactants and the products. I'm going to go back to my original color scheme. Carbon tetrahydride gas, commonly known as methane gas or natural gas, is bubbled through dish soap to create a mound of bubbles. When ignited in the presence of oxygen gas, a large amount of energy is released. So we need oxygen gas as a reactant. That's where I'm pausing for a moment to make sure that that's understood. But then it says a large amount of energy is released, which vaporizes the water and carbon dioxide products. So those are our products. The underlining green are our reactants. So let's start with our reactants. Our first reactant is carbon tetrahydride, commonly known as methane. So carbon tetrahydride, the prefixes tell us the formula. This is CH4. It's a gas, so I'm going to write that as a G. Now, when it's ignited in the presence of oxygen gas, so that means oxygen gas is going to be one of our reactants, but remember, oxygen is one of the 7 diatomic elements, so therefore O2, and it is a gas, so I'm going to put G. I'm going to separate these two reactants with a plus sign and indicate an arrow showing that these are going to produce products. Now we had to ignite it, so we do have to put, I'm going to put the delta sign there showing that a little bit of energy, heat energy, had to be applied to make this happen. Right. The products are told to us to be water and carbon dioxide. So let's write those out. Water, of course, you know is H2O. Carbon dioxide, you know, is CO2. Now, are these liquid or are these gas, or what state of matter are they? Well, the clue here is that they are vaporized. All right, so they are put into the gaseous form. So we are going to put them both as gases. I'm going to indicate a plus sign between those two products to show that those are two separate products. And lastly, I need to probably indicate that a fair amount of energy was released. So again, I'm running out of room, so I'm just going to put plus energy over here. Plus heat energy is released. Okay. So there it is, skeletal reactions. Skeletal reactions mean that you are properly writing the correct formulas for all the reactants and products. You're using the proper symbols to indicate plus signs in between reactants or in between products. An arrow to separate the reactants from the products. The states of matter, the solid, the liquid, the gas, and the aqueouses. You're indicating where heat energy is released or absorbed. And you're indicating if heat or a catalyst was needed. Now you'll notice that none of these particular reactions used a catalyst. So I was not able to give you an example here, but you'll see if you get a problem like that, it'll say the reaction is catalyzed by iron or some such descriptor. So when that's the case, you would put that symbol over the arrow. Right. Looking ahead, our next couple of lectures will be on starting from a skeletal reaction. We will now balance the equations, and we will classify them as one of 5 types of chemical reactions. All right, well that's it for this video lecture. We'll see you in the classroom.